So the next section is higher derivatives. So I'm going to start out with just a little motivation of the type of problem we're trying to solve. So a utility function, and this is a special type of function that shows up in economics, is a real valued function u of x, so I'm just going to call it u because it's utility, defined for real numbers. And the idea is it's going to help us compare wealth levels. And so basically, if u of x is greater than u of y, so x and y are some sort of wealth. So you could think of that as maybe income, maybe a payment from something. Then u of x is preferred. And so it's basically kind of telling me, let's see, well, I have some pictures, and that will hopefully make it a bit more clear. So some common utility functions are exponential utility. So it has a parameter a, it's greater than 0. Logarithmic utility, so it's just the log of my wealth level. Power rule, so it's b times x to the b, so it's sort of like a polynomial function. And quadratic, which is defined to be x minus bx squared for some number b greater than 0. And just to sort of help visualize, this is what they look like. So the actual value of the utility isn't important. But what is important is just how I'm going to compare things that are on this curve. So if I looked, for instance, at this logarithmic utility here, if I'm over on the left side, just a small increase in the x variable is going to give me a pretty big increase in utility. Whereas if I looked at, say, the right side of this power rule, the same size increase in x is going to give me a much smaller increase in my utility. And so where these things pop up is if you're trying to do something like planning for retirement. Having enough money just to survive every year in retirement, that gets you the most utility. You have to be able to pay for your house, pay for your food, pay your bills. That's, if you don't have that, you're going to have a really bad retirement. If you get up on the right-hand side where you start to have a lot of wealth, you already have a boat, do you really need an Airstream too? And so the particular utility function that I'm going to consider for the rest of this little lesson is the quadratic utility. And so normally when you're looking at utility functions, you want them to be non-decreasing. So you don't ever want to get to a point like I've drawn here, where if I was on this little bit of the quadratic utility function, I actually add more wealth and I'm somehow worse off. And so what you need to do is be able to find the maximum of this function. And I suppose, maybe if I was at a restaurant or something and I was putting food on the x-axis, there would be some point where I was pretty happy, and then if I continued to eat, I probably would be less happy. Maybe that would be a good example of this quadratic function. But generally, from just a purely economic point of view, you want them to be non-decreasing. So what you would want to do with this quadratic one, so you would want to find out where it gets to the very top. And then probably at that point, just say beyond that, the utility is just constant at that level. Oops. So what is the derivative telling us? And that's what I was trying to get at a little bit before when, if this curve is steep, so the derivative is telling us what is the slope of this curve at a point. So if the derivative is large, it means the curve is steep. It means that a little bit more wealth gives us a lot more utility. Whereas if I'm over here, a little bit more wealth hardly gives me any more utility. So that's the derivative is then going to give me sort of the relative change in utility for $1 more worth of wealth. And so now if I go back to my quadratic utility, I want to find a point where I'm at the top of this thing. And so the way I'm going to know I'm at the top, if I'm walking up a hill, I walk up the hill, and as I get closer to the top, it gets less steep until all of a sudden I'm going down the hill. And so at one point I'm going up, later I'm going down, somewhere in the middle it must have been flat. And so where it's flat, the slope of that tangent line is going to be equal to 0. So that means I want to find a point A so that the derivative is the slope of my tangent line, is going to be 0. And I'm going to call that point a critical point. And if my function has a local minimum, so that means that it either has a hump or a trough at a point A, then A is always going to be a critical point. And so if I sort of zoom in on my quadratic utility, so my u of x here is now the quadratic utility function, I find this point A, where it's flat here. Well, I can also take the derivative of u of x, and that's this descending line here that I've called u prime of x. And where that line crosses 0, that's where this point is, where the critical point is going to be. That's where the tangent line is going to be flat. So where this line is above 0, I have an upward sloping curve. When the derivative is less than 0, so below the x-axis, I have a downward sloping curve. And then you can do exactly the same thing if it were, this is just some arbitrary function that now has a local minimum. And so now where it's downward sloping, I have a derivative less than 0. Where it's upward sloping, I have a derivative greater than 0. And where this derivative actually hits the x-axis, that's where my critical point is going to be. And so the lesson we want to take away from this is if f prime of x is decreasing at A, so here f prime of x is going down at the point A, then I have a local maximum. So the function looks like the top of a hill. If it's increasing, so here the derivative is increasing when I hit the critical point, then I have a local minimum. And so most of the time what's going to happen when you're taking derivatives, you take a derivative of a function f of x, and you get f prime of x, and that's also a function. And most of the time, f prime of x is also going to be a differentiable function. And so you could, again, take its derivative. And so we're going to denote that by f double prime of x, which is just the derivative of f prime of x. And f double prime is called the second derivative of f of x. And I can also write it in Leibniz notation. So I take the first derivative of f of x. I think of this thing in the square brackets as a function, and I take that function's derivative one more time with respect to x. I can write this d squared over dx squared to mean take the second derivative in one step. And I can also use this notation, d squared f over dx squared, to mean the function that is the second derivative of f of x. And sometimes you'll also see this, so you just use a capital letter D. So df of x would be the first derivative of f of x. D squared f of x is the second derivative. And then there's no reason to stop at 2. So you can have as many higher derivatives as you want. Some notation that seems to be pretty common is you have f to the n, but the n is in parentheses, so that just means the nth derivative of the function f of x. Just like we had d squared dx here, we can have d to the n, dx to the n of f of x, or this capital letter d to the n of f of x. But that's only going to work if the one before that, so fn minus 1 of x, is a differentiable function. So as long as the derivative is a differentiable function itself, you can then take the derivative again and keep going. And so if we go back to our local maximum and local minimum picture, if I plot the first derivative, I get this decreasing line. If I plot the second derivative, that's just going to be the slope of the first derivative, but the first derivative is already a line, so its slope is going to be constant. So I just get a constant value here, u double prime of x. And so if f of x equals 0, sorry, f prime of x equals 0, so I have a critical point at a here, and f double prime of x, so that these I really ought to have put a in here. So if I evaluate f double prime at a as well, so if I look at a and go down to f double prime, that's less than 0, then that corresponds to a local maximum. So that allows me to classify this critical point as a maximum. Where if f prime of a were equal to 0, so here I have, now I'm talking about the graph on the right-hand side, I have a critical point because the derivative is equal to 0. But here, f of x, f prime of x is upward sloping. So f double prime of x is going to be a positive constant. So f double prime of a in particular is going to be greater than 0, and that's going to correspond to a local minimum. So these are called first and second order conditions. The first order condition says the derivative has to be equal to 0. Second order condition says second derivative less than 0. That gives me a local minimum. And then if the second derivative is greater than 0, sorry, second derivative less than 0 gives me a local maximum. Second derivative greater than 0 gives me a local minimum. So for functions like this, it's not too bad. You can just draw a picture, and it's usually pretty clear. But things get, can get a little bit more complicated. And then, especially if the function has several critical points, and you're looking for a maximum, you might want a way to weed out all of the local minimum. So for a financial example of this, suppose I have a certain amount of money, and I want to divide it into two assets. And my goal is to, so that is something called a portfolio. And I want to choose how much I'm going to put into each asset to maximize my expected return. And so basically what I want to do is, suppose I'm not allowed to short sell either one of those. So short sell means to sell something that I don't actually own. If I'm not allowed to do that, I have to put some amount of money into asset A and some amount of money into asset B, and those two amounts have to both be greater than 0 and sum up to my total amount of money. So the way I'm going to simplify that is just to say f of x is going to be defined on the interval 0, 1, and x is just going to be the ratio, or the fraction of money that goes into asset 1. So asset 1 gets x, asset 2 gets 1 minus x, and if I only consider x on the interval 0, 1, then both of those are going to be positive. More generally, you can do this on an interval a, b, but the 0, 1 will work for what I want to show off here. So if I want to find all of the minimum and maximum values of this function on 0, 1, the approach I'm going to use is first find all of the critical points on the open interval 0, 1. And I'm just going to evaluate f of x there. And I also need to evaluate f of x at a and b. So a and b are the endpoints. So I need to evaluate f of 0 and f of 1. And then the global maximum. So I can say what the global maximum is going to be because I know all of the points where that could occur on this interval 0, 1. Is just going to be the maximum of all of the points I find in steps 1 and 2. And then the minimum is going to be the minimum of all the ones I find in steps 1 and 2. And really it's step 2 that I'm trying to harp on here, because this is what could happen. So suppose this little tick over here is meant to be 1. If I have an expected return that looks something like this, I would find, just by using calculus, maybe these two orange points, which are the critical points. And then I would see, well, this one's positive, and this one's negative. And if I'm investing, I certainly don't want to invest in something that has a negative expected return. So I would probably choose this point here. But it turns out that in this particular example, the best choice would just be to put all of my money in asset 1 and none of my money in asset 2. And so this is actually a pretty common interview question. They'll set up some sort of payoff scheme like this, where if you don't check the endpoints, you're going to get the wrong answer. And then another step you could do is calculate the second derivative of f of x and evaluate it at the two critical points, and that would allow you to classify those as local minimum or local maximum.